Millisecond pulsars are some of the oldest neutron stars in the galaxy, yet they spin with the precision of a cosmic clock. In this calm journey, the story follows how a tired stellar remnant gets recycled by a companion, how its magnetic geometry shapes a steady beam, and how many of these clocks together can reveal the faint breathing of space-time itself. If this kind of quiet science-driven storytelling helps the mind unwind, please like the video, subscribe for more long-form space sleep documentaries, and leave a comment with the next topic to explore. A dead star can keep time with a steadiness that outlasts oceans and mountains. A millisecond pulsar is an old neutron star spun up until it turns about 500 times each second, and that speed becomes a long-lived cosmic clockwork. In that region, the star's crust forms a hard shell only a few steps thick on a city's scale. Beneath it, matter packs into a pressure gradient that rises sharply toward the center. A faint haze of charged particles drifts above the surface and clings to invisible field lines. Two narrow zones near the magnetic poles brighten more than the rest. Their brightness is not heat in the ordinary sense. It's a pattern of radiation guided by a strong magnetic field. The first payoff arrives quickly in a simple idea. The pulses do not come from something turning on and off. The pulses come from rotation that sweeps a beam across space. Light behaves as a moving stripe rather than a flood. The scene slows and becomes precise. A dark sphere rotates in silence. A thin rim of crust shows subtle ridges like cooled lava. Above it, the magnetic field channels particles into arcs that curve back toward the surface. A beam rises from one pole in a tapered cone. Another beam rises from the opposite side. The cones do not align with the spin axis. They lean. Each turn carries the beams around like a pair of slow lantern shutters. At a great distance, a signal would appear as a repeating tick when a beam points the right way. The steadiness can be extreme. The rhythm holds for ages, with only tiny drifts. That reliability matters because it turns violent stellar leftovers into probes of motion and gravity. The next payoff is hidden inside the word millisecond. A millisecond is 1,000th of a second. It is roughly the time between two frames in a high-speed flicker. For a star to finish a full rotation in that sliver of time, the equator moves fast. The motion stays bound because gravity is intense. The star is compact and heavy. The balance is delicate. A physical detail makes the balance feel real. Near the equator, the surface bulges slightly under centrifugal pull. The bulge is small in height. It is still a true shape change. The scale shifts from a thin crust feature to the star as a whole. Then it shifts again from one star to an orbit, where another object can change its fate. Many millisecond pulsars do not reach that speed alone. They are recycled. In that region, a close companion star can shed gas under strong tidal forces. The gas does not fall straight down. It spirals. It forms a flat disk that glows more at its inner edge. The disk is a moving gradient of density and temperature. The outer lanes drift slowly. The inner lanes whip around faster and crowd together. The main unlock appears. The disk carries angular momentum like a conveyor belt carries spin. As matter settles inward, it transfers that spin to the neutron star. The star accelerates over long time. The analogy is simple and new. It is like a smooth top on ice that speeds up when a gentle, steady swirl keeps feeding its motion. The top does not need a shove. It needs a long, quiet supply of twist. A second visual anchor arrives without haste. The disk looks like a dim vinyl record around a black bead. The inner ring brightens in a thin band. The band is not uniform. It shows a slight asymmetry where the magnetic field disrupts the flow. Matter lifts out of the disk into two funnel streams. Each funnel narrows as it approaches the surface. The funnels strike near the poles and paint hotspots that rotate with the star. Those hotspots anchor the beams. The pulses sharpen. The timing grows clean. The story now turns to a limit of intuition. The rotation is not seen directly. Only the beam pattern is sampled. If the beam never sweeps across a given line of sight, no pulses appear at all. The object can be spinning fast and still seem quiet. Observation is also indirect in another way. The interior structure cannot be resolved. The crust, the superdense core, and any layered transitions remain hidden behind a surface only tens of kilometers wide. Models infer those layers from mass and spin's limits. They cannot image the deep state of matter. The limit is both geometric and physical. Geometry controls whether a pulse is visible. Physics controls how close the star can spin to break up. This boundary is calm but strict. When rotation becomes too rapid, the equator would begin to shed material. The star approaches a threshold where gravity and centrifugal force nearly balance at the rim. The next payoff follows from that boundary. Millisecond pulsars cluster below that threshold. The ceiling is not a mystery. It is a structural constraint. It hints at how stiff the dense matter must be. A stiff interior resists distortion. A softer interior allows more bulge and reaches instability sooner. The scale shift becomes gentle again. It moves from microscopic interactions among neutrons to a global limit on a spinning sphere. The pulses remain the thread that ties these scales together. Each tick carries a memory of rotation. Each drift carries a memory of torque. The beam pattern also carries a clue about magnetic evolution. Recycled pulsars often show weaker surface magnetic fields than younger pulsars. The field still guides particles. It just does so with less braking power. The disk phase can bury or smooth parts of the field near the surface. Layers of new material can alter how field lines emerge through the crust. The physical detail is subtle. The polar caps can shrink. The hotspots can become smaller and more stable. The beam becomes narrower and more regular. In that region, the star feels less like a chaotic beacon and more like a metronome. The calm promise of the full journey becomes clear. The path begins with the basic lighthouse geometry. It then moves into how a binary disk feeds spin. It then opens into limits set by gravity and dense matter. The final visual anchor in this opening section slows everything down. A city-sized sphere turns in darkness. Two pale cones sweep across a faint fog. The fog has a gentle gradient and thins with distance. The sweep repeats with a rhythm too fast to count by eye. The rhythm is still orderly. Over long time that order persists. The next section turns closer to the birth of the neutron star, and the origin of its magnetic field then returns to how age and recycling reshape both. A millisecond rhythm begins as a slow-layered star loses its final support. The core collapses and the collapse locks in spin and magnetic structure that later shape every pulse. In the deep interior, distinct shells sit like calm strata. Lighter elements lie above heavier ones. The iron-rich center becomes a boundary where fusion no longer pays its energy debt. Pressure drops in a sudden way. Gravity takes over in a single direction. The first payoff appears in a simple rule. When size shrinks, rotation tends to speed up. The shrinking is not gentle. It races inward until matter presses against itself at nuclear scales. At this distance, the collapsing region resembles a dark sphere that tightens, while the outer layers lag behind. Ripples form where the infall changes speed. A steep density gradient grows near the center. The gradient is a real physical slope in matter, not a metaphor. It is a layered cliff inside the star. As the core compresses, protons and electrons combine into neutrons. Neutrinos stream out and carry away energy. The inner collapse can briefly halt when matter becomes stiff enough to resist. A rebound sends a pressure wave outward. That wave moves through material that is still falling inward. The wave can sharpen into a shock front. The shock is a thin boundary where conditions change abruptly. The next payoff comes from what remains after the violence. A neutron star forms as a compact object with a solid crust over a superdense interior. The crust is thin compared to the whole star. It cools and freezes into a lattice of nuclei. Below it, density rises again into a core where matter behaves unlike any familiar solid. The scale shift is smooth. It moves from a star wider than an orbit to an object that fits inside a small region of space. Yet the mass stays large. A typical neutron star carries about 1.5 times the mass of the Sun, like stacking one sun and another half sun into a sphere on a city scale. The shape responds. The equator becomes slightly wider than the poles. The surface is not a perfect sphere. A gentle bulge forms because rotation is now fast relative to size. In that same moment, magnetism is reshaped. Magnetic field lines present in the parent star are drawn inward with the collapsing material. Flux freezing means the field stays tied to the moving plasma. The field strengthens as the area it threads becomes smaller. The analogy is natural and quiet. It is like a river narrowing into a canyon. The current speeds up and the flow lines bunch together. The river does not gain water. It gains tightness. In the newborn neutron star field, lines bunch and intensify in a similar way. A visual anchor holds steady. Dark field arcs rise from one hemisphere and return to the other. They curve in a broad dipole-like pattern. Close to the surface, the arcs crowd together. Farther out, they open into space and become sparse. The field is not only a clean dipole. Higher-order twists can exist near the crust. The crust can trap stressed patterns like wrinkles in cooling rock. The next payoff arrives from this geometry. A rotating magnetic field tends to drag charged particles along. It also creates regions where electric fields appear along the magnetic lines. Those fields can accelerate particles and seed radiation. The magnetosphere forms as a thin plasma environment above the surface. It is not a solid shell. It is a dynamic region where charge densities adjust to the field and to rotation. Light behaves as guided emission, rather than free glow. The physical detail matters. The polar cap is a specific patch near each magnetic pole. It is defined by which field lines open outward, rather than closing back to the surface. That boundary can be imagined as a rim on the crust. Inside the rim, field lines return and trap particles. Outside it, lines can extend far and carry particles away. The rim can shrink or expand depending on spin and field strength. The scale shift returns. It moves from a rim only kilometers across to a structure that stretches outward many star radii. The calm also returns. After the explosion, the neutron star cools and spins down slowly. It loses rotational energy through electromagnetic torque. The rotation is not measured directly. The pulses, if present, carry the only clean signature. Some neutron stars are born with beams that sweep across space. Others never present a beam in a direction that would be noticed. This becomes a limit of observation that stays gentle but firm. The beam geometry can hide a pulsar completely. Timing alone cannot reveal a pulse that never crosses a line of sight. A second limit appears inside the star. The interior field and the state of dense matter cannot be resolved. Only indirect constraints exist. Models connect spin mass and deformation to an equation of state. Those models have uncertainties because the microscopic behavior is not sampled directly. The observation is precise. The interpretation remains inferential. Another payoff follows from this uncertainty. Millisecond pulsars later become valuable because their stability tests these models. A star that spins rapidly without breaking implies a certain stiffness inside. A star that shows tiny timing drifts can hint at subtle changes in shape or torque. The newborn phase sets the starting conditions. Recycled phases can then modify them. In that region, a binary companion can later add angular momentum through accretion. That process can bury parts of the magnetic field near the crust. It can also heat the crust and alter conductivity. The field that was amplified during collapse can be smoothed during recycling. The visual anchor shifts again, still calm. The surface shows faint banding from uneven heating. Two polar regions glow as small ovals. Above them, field lines rise in tight bundles. Farther out, the bundles fan into wider arcs. The arcs appear like a quiet canopy. The canopy rotates with the star. As it rotates, different regions of the magnetosphere come into alignment with the spin. The key idea settles into place. Collapse creates a compact object. Collapse also concentrates magnetic structure. Rotation then couples to that structure and organizes emission into narrow regions. The story now turns toward the beam itself. The next section follows how tilted magnetic geometry and plasma motion sculpt a pulse shape, then explains why some pulses stay so clean for so long. A pulse looks simple from far away, yet its shape is carved by delicate geometry close to the surface. The beam forms because a tilted magnetic field guides plasma and sculpts narrow emission zones that rotate like a lighthouse. In that region, the neutron star's surface is a hard crust with small height variations. Above it, a thin magnetosphere holds charged particles that prefer to slide along field lines. A magnetosphere is plasma controlled mainly by magnetic fields. It is like iron filings lining up around a hidden bar magnet. It is also like mist following invisible streambeds in a valley. It matters because it turns rotation into a focused signal instead of a broad glow. The first visual anchor is still and close. Two oval polar caps sit on the crust like pale patches. Each cap has a rim where open field lines begin. The rim is a true boundary. Inside it, lines loop back to the star. Outside it, lines stretch outward and never return nearby. The cap is not centered on the spin axis. It sits offset, and that offset is the quiet key. The star rotates. The magnetic pole traces a circle around the spin axis. The beam traces a cone whose openings depends on the field shape and on where emission forms. Light behaves as a narrow fan that sweeps space. A signal would appear as a tick only when the fan crosses the right direction. The first payoff arrives with a clear question resolved. A pulse is not a flash that begins and ends. It is a moving beam that briefly points the right way each rotation. That is why the same object can look steady in one direction and silent in another. Geometry decides the difference. The pulse profile also contains a second layer. It can show one peak or two. It can have a sharp edge or a rounded shoulder. Those shapes come from where along the field lines the emission occurs. Near the surface curvature is tight and the beam can be narrow. Higher up field lines spread and the beam can widen. The scale shift is gentle. It moves from a crust patch kilometers wide to a funnel of space that expands outward many times the star's radius. The concept of beaming becomes more physical. The beam is not a solid cone. It is a region where radiation is more intense. Within it, brightness can vary with angle like a soft gradient. The next payoff is an unlock about timing. A millisecond pulsar rotates about 500 times each second, like a hummingbird wing beat sped up into a blur. The rapid rotation makes tiny beam features repeat quickly. The repetition allows a pulse train to be averaged into a stable shape. Small irregularities in the magnetosphere can blur out. What remains is a clean template. That template becomes the clock face. The visual anchor widens. The star is now a dark bead within a faint rotating halo. Magnetic field lines arc outward like delicate ribs. A thin sheet of plasma gathers near a plane where opposing field lines brush. The sheet has a faint boundary where the plasma density changes. The boundary matters because it can influence where currents flow. Currents can create emission zones that are not exactly at the surface. They can form higher in the magnetosphere where field lines open. This adds a second concept. Aberration appears when rotation shifts the apparent direction of emission. Aberration is a direction shift caused by motion during emission. It is like rain slanting on a moving window. It is also like a shadow that leans when the light source moves. It matters because it skews pulse peaks and shifts arrival phases. In a fast rotator, those shifts can be noticeable even when the beam geometry is stable. The third concept stays implicit and does not grow heavy. The pulse is shaped by three quiet ingredients. Tilt sets the sweep. Emission height sets the width. Rotation adds subtle phase shifts. Each ingredient leaves a mark in the profile. The next payoff comes as a small map. A double-peaked pulse can mean two poles are seen. It can also mean one pole produces two bright zones at different heights. A broad pulse can mean emission is higher where field lines spread. A sharp leading edge can mean a narrow beam boundary crosses quickly. The pulse profile becomes a silhouette of invisible structure. Yet this silhouette also meets a limit of observation. Only a one-dimensional time series is received. Many different geometries can produce similar profiles. The tilt angle, the observer angle, and the emission height can trade off. This is a degeneracy. Degeneracy is different causes giving the same observed pattern. It is like hearing a note and not knowing which instrument plays it. It is also like seeing a distant light and not knowing its exact shape. It matters because geometry cannot be uniquely solved from pulse shape alone. Additional constraints are needed. Timing in binaries can help. Polarization can help. But even then, the magnetosphere's plasma state changes with time and complicates interpretation. The limit stays calm. The pulses can be precise. The model can still have multiple solutions. Another payoff follows from this limit. Millisecond pulsars stand out because their magnetospheres often appear quieter. Their surface magnetic fields tend to be weaker than in young pulsars. That reduces violent variability and helps stability. The beam becomes more predictable, the clock becomes more reliable, the scale shift softens again. It moves from microphysics of plasma to years of stable tick marks. Over long spans, tiny drifts in pulse phase can reveal orbital motion or subtle torques. The pulse is both a beam and a ruler for time. The section ends with a final visual anchor that is new and slow. A thin ring of faint emission traces around the star at a fixed altitude. The ring is not uniform. It brightens in two arcs where current density is higher. As rotation continues, the arcs sweep like quiet crescents. The next section follows how slow spin-down normally happens, then shows how recycling interrupts that aging and restores rapid rotation in old systems. Even a steady cosmic clock slowly loses its spin, as if time itself applies a gentle brake. A pulsar spins down because its rotating magnetic field carries energy away, and that drain grows clearer in the pulse timing. In that region, the magnetosphere is not a decorative halo. It is a working circuit of fields and charges. Magnetic lines curve out from the crust and open into space. Along those open lines, plasma can flow outward and carry angular momentum with it. The first payoff is a clean mechanism. Spin energy turns into electromagnetic power. The star's rotation slows as that power streams away. The slowdown is not a sudden event. It is a quiet, persistent torque. A physical detail anchors the torque. The open field line region forms a distinct cap with a rim. The rim marks where lines stop closing back. That boundary sets how much of the field participates in the outflow. A wider open region means more braking. A narrower region means less braking. The visual anchor is calm and new. A faint broad spiral of plasma extends away from the star. It is not a solid plume. It is a structured wind with a thin sheet where charge density changes sign. The sheet wavers slightly with rotation. It resembles a long ribbon that twists as it is unspooled. The analogy is quiet and unique. It is like a ceiling fan stirring air that drifts outward through an open doorway. The fan does not chase the air. It simply imparts motion that carries away. In the same way, the rotating field stirs plasma and sends energy outward. The next payoff arrives as a measurable consequence. The pulse period grows. The growth can be slow enough that only long timing records reveal it. Even without direct imaging, a signal would show a gradual drift in phase. Each drift encodes the braking torque. This is where millisecond pulsars become special. Their drift is often extremely small. The timing remains stable enough to act as a reference for motion in space. The one primary number settles the scale. A typical spin-down timescale for a millisecond pulsar can be about 1 billion years, like waiting for a continent to drift into a new shape. That number is not a stopwatch reading. It is a slow trend inferred from tiny changes. The scale shift is gentle. It moves from a pulse every few milliseconds to an evolution over deep time. The magnetosphere also changes as the star slows. The light cylinder moves outward. The light cylinder is where co-rotation reaches light speed. It is like a notional boundary beyond which rigid rotation cannot be maintained. It matters because it sets the outer size of the co-rotating field structure. As the star slows, that boundary expands. Field lines that were once forced open can become less stressed. The open region can shrink. The braking can weaken. Another payoff follows from that feedback. A pulsar can slow quickly at first and then more gently later. The clock does not simply wind down at a constant rate. It can ease into old age. The visual anchor shifts but remains concrete. Near the star, the polar caps appear as small ovals. Farther out, the field lines form a cage-like pattern. The cage opens into long arcs that stretch past the notional boundary. The plasma sheet beyond looks like a thin plane with a slight warp. The warp rotates. It casts a faint shadow in its own emission. The shadow is a physical contrast region, not a metaphor. It marks where density is lower. The next payoff comes from a subtle distinction. Not all losses come from the same channel. Some energy leaves as electromagnetic radiation. Some leaves with particles in the wind. Both remove angular momentum. The balance depends on field strength and plasma supply. Millisecond pulsars often have weaker surface fields than young pulsars. That reduces the braking for a given spin. It helps explain why they keep their rapid rhythm for so long after recycling. Yet a limit of observation appears here and stays gentle. The magnetic field strength near the surface is not measured directly. It is inferred from timing and from assumptions about torque models. Different magnetosphere configurations can produce similar spin-down rates. Plasma loading can change the effective torque without changing the dipole estimate. This is a modelling limit. Timing provides a precise slope. The translation into field strength depends on a chosen framework. Another limit is geometric. A pulse can remain stable even if some emission zones shift. The timing template can absorb small profile changes. That makes interpretation harder. A clean tick does not guarantee an unchanging magnetosphere. The next payoff answers a question that might linger. If spin down is inevitable, why does any old pulsar still spin fast? The answer is that spin down is a slow drain. Recycling can refill spin. After recycling ends, the drain resumes. A millisecond pulsar is not immune. It is simply starting from a high spin and losing it gently. The scale shift returns. It moves from the thin crust boundary that sets open field lines to the size of a magnetosphere that reaches far outward. It then moves again to the long time scale, where a tiny drift accumulates into a noticeable change. The analogy continues to hold without repetition. The doorway outflow carries away motion steadily. The fan keeps turning. The room remains calm. The star's rotation remains calm too, even as it slowly diminishes. The section ends with a soft transition that sets the next checkpoint. Spin down describes how clocks age in isolation. The next section turns to the opposite process. It follows how a companion's flowing gas forms a disk, and how that disk transfers angular momentum to rebuild a millisecond rhythm. A fast spin can return to an old neutron star through a slow, orderly flow of gas. Recycling happens when a close companion overfills its gravitational boundary and feeds a disk that transfers angular momentum into the star. In that region, the companion is not a round sphere. It is stretched into a teardrop shape by tides. A narrow neck forms where gravity between the two objects nearly balances. Gas drifts through that neck in a thin stream. The stream does not fall straight down. It arcs and misses the neutron star at first. It wraps around and begins a circular path. The first payoff arrives with a simple reason. A miss is what makes a disk. The stream carries sideways motion that cannot vanish instantly. The gas spreads into an accretion disk. An accretion disk is a rotating disk of infalling matter. It is like a river bend that keeps curving and feeds a persistent whirlpool. The river does not need to be pushed. It only needs a steady inflow at an angle. The disk forms a visible gradient. The outer lanes are cooler and dimmer. The inner lanes are hotter and brighter. Between them there is a smooth change in brightness. The primary visual anchor settles into place. The companion hangs close as a dark oval. A faint stream of gas glows as it arcs across the gap. It strikes the outer rim of the disk and raises a bright crescent. The crescent is a standing ripple where fresh material hits. The disk itself looks like a thin plate with a sharp inner edge. The edge is not a cliff in space, it is a boundary set by the neutron star's magnetic field. Inside that boundary, flow cannot stay in a flat orbit. It is guided upwards into funnel shapes. The next payoff unlocks the spin-up process. The disk carries angular momentum inward. Friction and turbulence move angular momentum outward. Mass moves inward. As each ring of gas drifts closer, it spins faster. That is not a choice. It is orbital mechanics. The neutron star receives the inner flow. It also receives the flow's angular momentum. The star's crust responds by accelerating. The spin increases over a long interval. The one primary number keeps the scale safe. The total transferred mass can be about 1/10 of the Sun's mass, like adding several dozen Earth masses in slow motion. That amount is small compared to a star. It is large compared to any planet. The scale shift is gentle. It moves from a stream a few star diameters wide to a change that matters for billions of rotations. The disk is the middle ground. It translates orbital motion into stellar spin. A physical detail keeps the disk real. Near the inner edge, the gas orbits so quickly that it becomes a smooth blur. The bright lane narrows into a ring. The ring has a slightly sharpened rim where temperature changes quickly. That rim is a gradient in heat and density. It sets where radiation is strongest. Light behaves as a map of flow. Brighter means hotter and closer. Dimmer means cooler and farther. The next payoff answers why the star does not spin up forever. A balance vaguely at good point appears. The neutron star has a magnetic field that co-rotates with its crust. When the disk's inner edge orbits faster than the star torque adds spin. When the star rotates faster than the inner disk torque can resist further spin-up. This is an equilibrium. The disk and field find a pace where net torque becomes small. The idea stays calm. A moving belt can accelerate a wheel only until speeds match. The belt here is the inner disk. The wheel is the star. The coupling is magnetic, not mechanical. In that region, field lines thread the inner disk like faint arcs. They do not cut through freely. They can twist. They can store stress. When the twist becomes too large, reconnection can occur. That changes how torque is applied. The visual anchor shifts within the same scene and remains unique. A thin set of luminous filaments rises from the inner ring into two funnels. The filaments curve towards small polar caps. At the cap edges, a bright oval forms with a darker center. The darker center is a shadowed patch where infall is less intense. The ovals rotate with the star. Their shape can stay steady for long spans. That steadiness makes a millisecond pulsar later appear calm. The next payoff is a direct link to pulse stability. Recycling tends to reduce the effective surface magnetic field. Accreted layers can bury parts of the field in the crust. That burial smooths small-scale structure. A smoother field produces more stable emission zones. The clock face becomes cleaner. Yet a limit of observation enters and stays explicit. The disk cannot be resolved in detail at these distances. Only integrated light and timing changes are available. Many disk structures can produce similar brightness variations. The exact inner edge location is inferred from models. The torque history is also inferred. Spin changes can be measured precisely. The conversion from spin change to mass transfer rate depends on assumptions about magnetic coupling. This is a modelling limit. Timing can be exact. The interior story remains indirect. The limit of intuition appears beside it. Dense matter inside the star resists deformation. That resistance affects how fast the star can spin without shedding mass at the equator. The internal stiffness cannot be sampled directly. It is deduced from global behaviour. The next payoff comes from combining these limits. Even without a resolved disk, the recycled outcome is recognisable. A millisecond pulsar has rapid rotation and a comparatively weak surface field. It also often sits in a tight orbit where timing shows gentle delays. The recycled state is a calm solution to an energetic past. The stream feeds the disk feeds spin. The magnetosphere shapes the final torque. The scale shift widens again. It moves from a thin neck of gas to an orbit measured in hours. It then moves from hours to a span of millions of years of steady transfer. The star's spin changes by tiny steps each orbit. Over deep time, those steps accumulate into a millisecond rhythm. The primary analogy returns without repetition. The river bend keeps feeding the whirlpool. The whirlpool deepens and tightens. It does so without noise in the story. The final image holds steady. The teardrop companion remains close. The gas stream remains a narrow arc. The disk remains a flat, luminous ring with a bright crescent where the stream impacts. The funnels remain two faint bridges into the polar caps. The next section moves closer to the disk's inner boundary and the magnetic interface. It follows how heating layering and field burial reshape the pulsar into an even steadier spinner. The boundary where a disk meets a magnetic field is quiet, yet it decides how a neutron star is rewritten. The recycling process reshapes the star by funneling matter onto polar caps and by pressing magnetic structure down into the crust. In that region, the inner disk does not simply end. It thins into a sharp rim where magnetic pressure rivals the disk's push. The rim looks like a narrow ring with a steep brightness gradient. Just outside it, the disk remains flat and smooth. Just inside it, the flow lifts out of the plane. Two funnel streams form. They curve along field lines toward the surface. The first payoff appears as a direct link. The magnetic field does not block accretion, it redirects it. This redirection concentrates heating into small regions. Those regions become stable anchors for emission later. The primary visual anchor settles into a new scene. The neutron star's surface shows two bright crescents near the poles. Each crescent has a sharp edge where the infalling stream strikes. Behind that edge, a darker wake spreads where the flow has already cooled. The hot region is not a point. It has a shape set by the field geometry. A thin boundary outlines it like a coastline. The coastline shifts slightly as the accretion rate changes. The analogy is calm and unique. It is like snow drifting onto a roof ridge. The wind funnels snow into two steady piles. The roof stays the same. The piles change the roof's profile and weight distribution. In the same way accretion funnels matter into caps and adds layers to the crust. Those layers matter because they change how magnetic field lines emerge. Field burial becomes the second core concept. Field burial is suppression of surface field by added conductive layers. It is like covering a faint pattern under fresh paint. It is also like pressing a spring under a cushion so its shape is hidden. It matters because a weaker surface field reduces braking and helps fast rotation persist. The mechanism stays physical. As new material piles up, it spreads sideways under gravity. It forms a new layer over the old crust. Electrical currents in the crust carry the magnetic field. When conductivity is high and the layer is thick, the field can be pushed deeper. The surface dipole can look smaller even if deeper fields remain. The first micro payoff follows. Recycling does not need to erase magnetism. It only needs to change what reaches the surface. A millisecond pulsar can still guide plasma and create beams. It does so with a smoother, quieter field. This smoothing can reduce noisy variations in pulse shapes. The clock becomes cleaner. The third concept stays light and practical. Torque depends on where the inner disk sits relative to the rotating field. When the disk rim is outside a certain radius, inflow adds spin. When the rim moves inward, the spin-up can become stronger. When the star spins faster, the coupling can weaken. A calm balance is approached. This balance point changes as the field changes. A weaker field allows the disk to come closer. That can increase spin-up efficiency. The scale shift is gentle. It moves from a rim only a few star radii out to the long history of mass transfer that alters crust layering. The one primary number keeps the scale stable. The polar cap size can be about 1 kilometer across, like the width of a small town. That is tiny compared to a star. It is still large compared to any ordinary patch of ground. The number is not for precision, it is for imagination. A cap of that size can carry most of the accretion heating. It can also anchor the emission that later becomes a pulse. The next visual anchor appears on cadence. The inner ring of the disk glows as a thin band. Two filamentary streams rise like translucent ribbons. They narrow as they descend. At the surface, they spread into crescents with bright leading edges. The edges are physical shock boundaries wherein falling gas decelerates. Heat diffuses away into the crust. Over time, this repeated heating can soften compositional gradients in the upper crust. It can also create a layered structure of ashes from nuclear burning. The payoff arrives as a clear consequence. Layering affects conductivity. Conductivity affects how quickly buried magnetic fields can re-emerge after accretion ends. If conductivity is high, the field can remain suppressed for a long time. If conductivity is lower, or if layers crack, some structure can return sooner. This does not require a dramatic event. It is a quiet diffusion problem in dense matter. The limit of intuition arrives softly. It is hard to picture magnetic burial because field lines are not objects. They are a description of force. The burial is not a blanket laid on top. It is a shift in where currents flow. This is why intuition can mislead. Field strength is often treated as a single number. The real field is a three-dimensional structure. It can be complex near the crust. The limit of observation is also clear and specific. The buried field cannot be mapped directly. Only pulse behavior and spin-down trends are observed. Many different internal field configurations can produce similar external dipoles. Models can fit timing. They cannot uniquely reveal the hidden currents. The outcome is still useful. The uncertainty defines a range rather than a single answer. Another payoff follows from that range. Recycled pulsars tend to sit in a stable regime, where the surface field is weaker and the spin is fast. That combination makes their timing exceptionally regular. It also makes their emission regions compact and persistent. The caps remain small, the beam remains narrow. Profile changes become subtle. The clock becomes reliable over long spans. The section keeps its calm cadence with another concrete detail. The accreted layer settles under gravity and forms a smooth shell. The shell has a compositional gradient that steepens with depth. Lighter nuclei sit above heavier ashes. The gradient changes how heat moves. Heat can spread sideways and blur the cap edges. It can also leak inward and alter the crust's mechanical stress. Stress can accumulate at boundaries between layers. That matters later when the star spins rapidly and wants to bulge. A final scale shift widens from a 1 kilometer cap to deep time. Recycling can last millions of years. During that time, each orbit adds a little spin and a little layer. The layered crust becomes a record of repeated infall. When the stream weakens and the disk fades, the star is left spinning fast with a modified surface field. The ending transition stays gentle. The next section follows how that spin-up reaches a ceiling. It explores the balance between gravity rotation and deformation, then returns to what the ceiling reveals about dense matter. A millisecond spin has a ceiling that comes from shape gravity and the quiet strength of dense matter. The spin-up stops near a limit where the equator nearly lifts, and that limit reveals how rigid a neutron star can be. In that region, the surface is a solid crust that resists stretching. Rotation still pulls outward. The pull is strongest at the equator. A slight bulge appears. The bulge is not decoration. It is a measurable distortion in the star's figure. The first payoff arrives as a clear constraint. Faster spin requires stronger inward gravity or stronger internal stiffness. If either is insufficient, the equator begins to shed material. The physics is simple in outline. The details are subtle in the interior. A physical detail makes the limit tangible. The equator becomes wider than the poles. The surface gravity becomes slightly weaker at the rim. The crust experiences shear stress as it tries to hold a rounded shape against flattening. The primary visual anchor is calm and new. The neutron star is seen as a dark, slightly flattened sphere. A thin pale band circles the equator where the surface bulge is greatest. The band is not bright because of heat. It is a geometric highlight that marks curvature. Above it, faint field lines arc outward. They remain tied to the rotating crust. The analogy is quiet and unique. It is like a spinning lump of soft clay that flattens into a wider disk. The clay can spin faster only if it is firmer. If it is too soft, it spreads and loses form. The neutron star is not clay. The analogy captures the relationship between stiffness and shape. The next payoff links the limit to recycling. Accretion adds angular momentum until the star nears this structural boundary. The disk can still feed spin, the star can still accept it. The star's own shape becomes the bottleneck. That is why many millisecond pulsars cluster below a maximum frequency. The one primary number keeps the scale grounded. A practical upper spin for many neutron stars is around 1,000 turns each second, like a drum roll condensed into a steady hum. That number is a round guide, not a promise. It sets the sense of proximity to breakup. The scale shift is gentle. It moves from a single turn and lasting a millisecond to an evolution over millions of years of spin-up. At the far end, the limit is reached without drama. The star simply stops gaining speed efficiently. The second core concept is the equation of state. An equation of state links pressure and density in dense matter. It is like a recipe that tells how hard matter pushes back when squeezed. It is also like a mattress that can be firm or yielding under the same weight. It matters because it sets the star's radius and its resistance to deformation. A stiffer interior supports a larger star for the same mass. It also changes how the star bulges under rotation. The third concept stays minimal and concrete. Deformation can create a tiny asymmetry in mass distribution. That asymmetry can radiate energy away and act as an extra brake. Even a small bump can matter at high spin. The bump could be a mountain on the crust. It could be a slight internal density wave. The exact cause is uncertain. The effect is a steady drain that competes with spin-up. The next payoff explains why this matters for observation. A stable millisecond pulsar that remains below the ceiling implies that deformation and braking are limited. It suggests constraints on how large asymmetries can be. It also constrains how the crust and core share stress. The visual cadence continues. The equatorial band is seen again. It is joined by faint concentric contours that trace gravitational potential. Those contours are closer together near the star. They spread outward in a smooth gradient. The contours are not visible lines. They are a way to imagine the field as layered shells. Light behaves as if it climbs out of a deep well. Time itself is slightly slowed near the surface. This is not the focus here. It is part of the quiet setting. The limit of intuition arrives softly and explicitly. It is tempting to imagine a rigid ball with a simple speed limit. The interior is not a simple solid. The core can behave like a superfluid. A superfluid is a fluid that flows with almost no viscosity. It is like a perfectly smooth bearing that lets layers slide with little friction. It matters because different layers can rotate at slightly different rates. That complicates how spin and stress are shared. The crust can lock to the magnetosphere. The core can lag or lead by a tiny amount. This makes the true stability limit harder to picture. The limit of observation is also clear. The internal state cannot be imaged. The equation of state is inferred from mass and radius estimates and from spin behavior. Those estimates have uncertainties. Pulse timing is precise. Radius measurements are not always precise. Models must connect external timing to internal source, internal stiffness. Different equations of state can fit the same limited set of constraints. The limit is not ignorance. It is a bounded ambiguity. Another payoff follows from this ambiguity. The spin ceiling becomes a filter. Only stars with sufficient stiffness and suitable magnetic coupling can reach the fastest spins. Recycling can spin many stars up. Only some reach the highest rates. This selection explains why the population looks clustered. It also explains why millisecond pulsars are valuable laboratories. Their mere existence narrows the range of possible dense matter behavior. The section keeps the calm arc by returning to a physical contact point. The disk's inner rim couples torque into the star through magnetic stresses. As the star approaches the ceiling, slight changes in rim position can switch the torque from spin-up to balance. The rim forms a thin ring with a sharp edge. That edge is a real gradient in pressure and density. The gradient sets how field lines thread the disk. The final payoff is immediate. The ceiling is not a wall. It is a set of gentle feedbacks between shape stiffness and torque. The star slows its approach and settles. The millisecond rhythm remains. The next section moves from limits to signatures. It follows how accretion heating and surface layers can trigger flashes and subtle changes, then shows how those changes still fit within a remarkably stable clockwork. A surface only a few steps thick on a city scale can still flash with sudden precision. Accretion builds a thin fuel layer on the crust, and that layer can ignite in a rapid burn that briefly reshapes the pulsar's light. In that region, infalling gas does not settle evenly across the star. Magnetic funnels guide it toward polar caps. Some of the flow spreads sideways after impact. It forms a shallow ocean on the crust. The ocean is not liquid water. It is a dense layer of ions and electrons. It has a temperature gradient that is steep near the hotspots. It cools outward into darker regions. The first payoff arrives as a simple mechanism. Fuel accumulates until pressure and temperature reach a threshold. Then nuclear burning runs away in a thin sheet. The sheet races across the surface and releases energy as a brief burst. The primary visual anchor is calm and concrete. The star is seen as a dark sphere with a faint equatorial flattening. Near one pole, a bright patch expands into a glowing oval. A thin, luminous front outlines the edge of the burn. Behind that front, the glow is smoother and more uniform. The edge is a real boundary where reactions are active. The boundary curves around the star like a moving coastline. The analogy is quiet and unique. It is like frost spreading across a cold window. The frost front advances in a thin line. The glass behind it looks uniformly pale. The window does not change shape. Only the surface pattern changes. In the same way, the burst does not change the star's rotation. It changes surface emission and heating. The second core concept is the thermonuclear burst. A thermonuclear burst is rapid nuclear burning in a surface layer. It is like a match head flaring after enough heat builds. It is also like dry grass that ignites once a critical dryness is reached. It matters because it reveals how fuel piles and how heat moves through the crust. The third concept stays simple and directly tied to timing. Hotspots and surface brightness changes can alter pulse shape. When a burst brightens part of the surface, the beam pattern can shift. The pulse profile can broaden. It can gain an extra shoulder. Timing remains regular, yet the shape changes. The next payoff explains why this is still useful. Profile changes reveal geometry. A broader pulse can mean a larger bright region. A shifted peak can mean a different dominance between two emitting zones. The burst becomes a temporary flashlight that illuminates the surface map. The one primary number anchors the timescale. A burst can last about a minute, like a single calm breath cycle repeated many times. That is short compared to the star's spin. It is long compared to a millisecond tick. The scale shift is gentle. It moves from a rotation repeated hundreds of times each second to a minute-long event that smooths over many rotations. The burst front itself is a scale shift. It's a thin boundary moving across tens of kilometers. It is also a deep time hint. Repeated bursts over years can change the ash layering in the crust. Layers can build like sediment. Each burst leaves behind heavier nuclei. Those ashes sink slowly. They form compositional gradients. The gradients matter for conductivity and for magnetic burial persistence. The visual cadence continues. The burning front wraps around the star and meets itself. The bright region becomes a near uniform glow with a slightly brighter rim near the pole. A faint shadowed band remains near the equator where fuel was thinner. The shadow is a contrast region. It is not a physical depression. It is a brightness gradient that hints at uneven deposition. Another payoff arrives from the heating. The crust can respond by expanding slightly. Expansion changes the moment of inertia by a tiny amount. That can cause a slight shift in rotation rate. The shift is subtle. The key point is calm. Even tiny changes can be detected in timing when stability is high. Yet this is also where a limit of observation appears. The interior response cannot be watched directly. Only changes in pulse shape and phase are measured. It is hard to separate a true spin change from a shift in emission geometry. A pulse arriving earlier could mean faster rotation. It could also mean a bright spot moved in longitude. This is a degeneracy in interpretation. It is a modelling limit tied to geometry and to unknown emission physics. The limit of intuition appears beside it. A burst feels like an explosion. In this context, it is a thin layer event on a dense star. The total structure barely notices. The rotation remains almost unchanged. The magnetosphere remains largely intact. The burst is a surface pattern superimposed on a stable clock. This contrast is easy to miss if the word burst dominates the imagination. Another payoff follows as clarity. Bursts are not random fireworks. They are threshold behavior in a layer. They appear when supply and cooling create the right conditions. They can repeat with some regularity when accretion is steady. The repetition becomes another probe of the system's state. When accretion slows, bursts can fade. When accretion is strong, stable burning can replace bursts. The story remains quiet and procedural. The surface layer becomes a thermostat. The crust becomes a heat sink. The magnetosphere becomes a lens that turns brightness into pulses. The physical detail returns to keep the scene grounded. The burning front is not smooth. It can have a slightly jagged edge due to local variations in fuel depth. The edge can slow near cooler regions. It can speed up near hotter regions. This creates a faint asymmetry in the expanding glow. The asymmetry can imprint a temporary distortion on the pulse profile. That distortion can relax as the surface cools. Cooling itself is a gentle gradient that slides across the star. The scale shift widens again. Cooling occurs over minutes. The crust retains heat over hours or longer. Over years, repeated events build a layered ash profile. Over millions of years, recycling modifies the magnetic field and the spin. The burst is a brief note in a long composition. The ending transition stays soft and forward-looking. The next section returns to the clock aspect and theirs. It follows how timing in binary orbits encodes motion through subtle delays, and how those delays become a map of mass and geometry without ever resolving the system directly. A millisecond clock in a binary reveals its orbit through delays so small they feel like silence. The timing shifts because the pulsar moves around a companion, and that motion changes the path length and the flow of time. In that region, the pulsar does not sit still. It traces an ellipse around the system's center of mass. The radio beam or high-energy beam sweeps steadily. The pulses leave at nearly regular intervals. The travel distance to a far location changes as the pulsar moves toward or away. Light behaves as a messenger that must cross a slightly longer or shorter route. The first payoff is immediate. The orbit writes a signature into the pulse arrival times. When the pulsar is closer along the line of travel, pulses arrive earlier. When it is farther, pulses arrive later. The effect is a gentle wobble in timing that repeats with the orbital period. The primary visual anchor is new and slow. Two dark objects circle each other. Around them a faint dustless emptiness holds a thin ribbon of orbit traced only by imagined points. The pulsar's path shows as a smooth loop. At one side of the loop, the pulses would arrive slightly compressed. At the other side, they would arrive slightly stretched. The analogy is calm and unique. It is like a lighthouse on a floating buoy that rises and falls with a slow swell. The lamp flashes steadily. The distance to the shore changes slightly with each swell. The flashes reach the shore sooner or later by a small amount. The buoy does not change its flashing rhythm. The travel time changes the perceived rhythm. In the same way orbit changes the apparent arrival times, without changing the intrinsic spin. The second core concept is the Romer delay. A Romer delay is a timing shift from changing light travel distance. It is like hearing a metronome across a room while walking closer and farther. It is also like a siren's arrival lag without any change in its source. It matters because it gives the projected size of the orbit. The third concept stays minimal and adds depth without clutter. Gravitational time dilation can add an extra delay. Near the companion space-time is slightly deeper. Pulses passing through that region can arrive later than expected. This delay is not from extra distance. It is from time running differently in a gravitational potential. The idea is quiet. It is a small correction layered on a larger geometric wobble. The one primary number anchors the scale. The timing wobble can be about 1 second, like a single calm pause inserted into an otherwise steady sequence. That second is spread across an orbit. It is not a missing pulse. It is a smooth advance and retreat of arrival times. The scale shift is gentle. It moves from millisecond ticks to a 1 second sweep across an orbital cycle. It then widens again. Over years, the orbit itself can change as angular momentum is lost. The timing can reveal that change as a slow drift in orbital period. The first micro payoff answers how mass enters the story. The orbit's shape and the timing wobble encode the mass function. The mass function is a relation between masses and orbital motion. It is like inferring the weight of 2 stones tied by a string from how the string curves in motion. It matters because it constrains the companion mass without seeing the companion surface. Another payoff follows through a clean piece of geometry. If the orbit is tilted close to edge-on, a signal would pass near the companion at conjunction. Additional delays can appear when pulses traverse the companion's gravitational well. The delay is small, it can be precise. It offers a way to estimate the companion's mass. The visual cadence stays slow. The orbit is imagined as a thin oval. A faint cone of pulses sweeps outward from the pulsar. At conjunction, the cone grazes the region near the companion. A subtle shadowed corridor appears in the timing model. It is not a physical shadow. It is a region of delayed arrival that aligns with the companion's position. A concrete physical detail grounds the geometry. The companion can be distorted into a teardrop due to tides. The tidal bulge points toward the pulsar. That bulge can also shed a thin veil of plasma in some systems. The plasma can scatter or absorb pulses. Scattering broadens pulse shapes by adding a faint tail. The tail is a physical consequence of multipath propagation through a variable medium. The next payoff arrives. Timing is not only about clocks, it is also about the space between objects. When scattering varies with orbital phase, it maps the distribution of plasma in the system. The map is indirect, it is still informative. The limit of observation now appears clearly. The orbit is not seen as a picture, it is reconstructed from arrival times. The reconstruction depends on an assumed timing model. Different combinations of inclination and masses can fit the same delays. This is a degeneracy. It is a limit of inference rather than a lack of data. Additional effects can break it. Some systems have eclipses, some have measurable gravitational delays, many do not. The limit remains calm and explicit. Timing can be extremely precise. Geometry can still remain partly uncertain. The limit of intuition appears beside it. It is tempting to think a 1 second wobble is large. It is large compared to a millisecond. It is tiny compared to the total travel time across space. The wobble is a subtle ripple on a vast baseline. The baseline is the long, light path through space. The wobble rides on top like a small wave on a deep ocean. This perspective keeps the scale shift gentle. The next payoff answers why millisecond pulsars are favoured for this work. Their pulses are stable. Their profiles can be averaged into clean templates. Small arrival shifts can be measured without confusion from intrinsic noise. When profiles change due to plasma or bursts, those intervals can be modelled or excluded. The clock remains strong. The orbit becomes visible in time. Another visual anchor appears on cadence and stays within the same primary scene. The orbital ellipse is traced again. A series of pulse markers forms a dotted line in time. The dots bunch slightly on one side and spread on the other. The pattern repeats. The repetition is the orbit speaking. The section closes with a gentle forward motion. Orbital timing reveals masses and geometry. The next section moves to more subtle uses. It follows how long-term timing can sense tiny deformations and energy loss mechanisms, then returns to what those signals imply about dense matter in the long life of cycled pulsars. A millisecond pulsar seems perfectly smooth, yet tiny imperfections can leave a faint fingerprint in time. Long-term timing can sense subtle deformations and slow energy drains that remain invisible in any direct image. In that region, the neutron star is a dense sphere with a solid crust and a hidden interior that can flow in unusual ways, even after recycling stresses persist. Rotation flattens the star. Magnetic structure pulls on the crust. Accreted layers settle and cool into compositional gradients. Each gradient is a physical slope in density and conductivity. The first payoff arrives as a quiet principle. A rotating body that is not perfectly symmetric can lose rotational energy through additional channels. The symmetry does not need to be broken by much. A tiny offset in mass distribution is enough to matter over long spans. The primary visual anchor is new and slow. The star rotates with a faint equatorial bulge. Near one latitude, a shallow ridge arcs for a short distance like a low seam in rock. The ridge is only a slight height change. It is still a real deformation in the crust. Above it, field lines curve in a slightly uneven pattern. The unevenness is subtle. It is the kind that would not show in a silhouette. It can still affect the star's spin evolution. The analogy is calm and unique. It is like a spinning coin with a small dent on its edge. The coin still spins. The dent makes the motion bleed energy a little faster and in a slightly different way. The coin does not break. It simply settles sooner. In the same way, a tiny crustal mountain or internal distortion can add a gentle break. The second core concept is gravitational radiation. Gravitational radiation is ripples in space-time from changing mass distribution. It is like faint waves spreading across a perfectly still pond. It is also like a barely visible tremor passing through a calm sheet of ice. It matters because it carries energy away without any light. For a steadily rotating deformation, the ripple pattern is periodic. It can act as the steady drain on spin. The third concept remains minimal and stays tied to what timing can reveal. A timing residual is the difference between observed and predicted pulse arrival times. It is like a small error curve after fitting a smooth trend. It is also like hearing a beat that slowly drifts against a reference tone. It matters because residuals can indicate unmodeled torques, orbital changes, or subtle shape effects. The next payoff explains how a deformation shows up. If electromagnetic braking alone cannot explain the measured spin down, an extra drain is implied. Gravitational radiation is one possible drain. Another is internal friction between layers rotating at slightly different rates. A superfluid interior can decouple and then recouple. That can cause small changes in spin behavior. The story stays calm and grounded. The key is that timing traces the net torque. It does not reveal the unique cause by itself. The one primary number anchors the scale of subtlety. The fractional asymmetry can be about 1 part in a billion, like a single grain of sand compared to a large beach. This number is a safe order of magnitude guide. It communicates that the deformation is tiny. It can still matter because rotation repeats so many times. The scale shift becomes gentle. It moves from a crust ridge measured in centimeters to a timing record that spans years. It then widens again to the full lifetime of a recycled pulsar. Over that lifetime, tiny drains accumulate into measurable spin down. The visual cadence continues with another concrete scene. The star's surface shows a patchwork of slightly different compositions from past accretion. The patchwork is not colourful. It is a map of conductivity and heat flow. A faint temperature gradient leaks outward from old polar cap regions. The gradient is smooth. It influences where plasma is supplied to the magnetosphere. That in turn can shift the pulse profile slightly over time. Another payoff arrives. Profile changes can mimic torque changes in timing. A shift in the effective emission region can move pulse phases. A clean model can mistake this for a true spin change. This is a limit of observation that must be stated clearly. The timing precision is high. The pulse template is not perfectly constant. The observable is not a rigid tick mark. It is a shaped wave that can drift. The limit is not fatal. It simply requires caution. Timing residuals can be interpreted only after accounting for profile evolution. The limit of intuition appears in a quiet way. It is tempting to imagine a pulsar as a perfect metronome with a single knob called spin. In reality, magnetosphere state surface heating and internal coupling all act together. The metronome is excellent. It is not absolute. Small hidden changes can shift the apparent beat by tiny amounts. The next payoff clarifies what can still be learned. When a stable millisecond pulsar shows a steady spin down and stable profiles, electromagnetic torque is likely dominant. When residuals show a particular periodicity tied to rotation, a persistent asymmetry is suggested. When residuals show sudden steps, internal coupling events are suggested. Each pattern is a clue. None is a full picture. The clue is still valuable because it constrains what dense matter can do. The physical detail returns to keep the story tangible. The crust has a yield strength. Under spin and magnetic stress, it can crack or relax. If a ridge forms or shifts, the quadrupole moment changes slightly. That change can alter any gravitational radiation drain. It can also alter spin down through changes in moment of inertia. The magnitude is small. The effect accumulates over time. Another visual anchor appears on cadence and stays within the primary scene. A faint ring of magnetospheric plasma sits near the equator. Its density is slightly higher above the ridge region. The ring is not a hard boundary. It is a gentle band of enhanced charge. It rotates with the star. It suggests a coupling between surface conductivity patterns and plasma supply. The payoff is immediate. Even when the object cannot be imaged, timing can feel these couplings as small variations in spin down and profile stability. The section then widens toward the larger arc. The best millisecond pulsars become laboratories for gravity and dense matter. Their steadiness sets a baseline. Deviations from that baseline reveal additional physics. The ending transition remains soft and forward. The next section widens from single systems to environments where such binaries form and survive. It follows how dense star swarms reshape orbits and increase recycling pathways, then returns to what those environments add to the story of millisecond clocks. In some regions of the galaxy, old stars gather so densely that orbits become a quiet form of weather. A globular cluster core acts like a gravitational mixing bowl that repeatedly reshapes binaries and creates many recycled millisecond pulsars. In that region, stars are not spaced like a calm neighborhood. They are packed into a bright center with a steep brightness gradient. The light thickens toward the core and thins into a faint outer halo. Paths curve in many directions. Small changes in distance decide which star influences which orbit. The first payoff comes from a simple outcome. Close passages between stars can alter binaries without any collision. Gravity alone can trade partners and tighten orbits. That is why globular clusters produce an unusually large share of millisecond pulsars. The primary visual anchor is slow and wide. A spherical cluster hangs like a soft lantern of starlight. The center is a dense glow with a sharp edge that fades outward. Inside that glow, a few tight binaries trace tiny loops. Around them, single stars drift on longer arcs. The arcs overlap like faint threads in a woven ball. No one thread is planned. The weave still has structure. The analogy is natural and unique. It is like seeds suspended in a slow eddy within a river bend. The seeds do not strike each other often. They still exchange places and form the temporary pairs as the flow brings them close. In the same way, stars in a cluster core drift and occasionally pass close enough for gravity to rearrange an orbit. The key mechanism is an encounter. An encounter is a close gravitational meeting that changes trajectories. It is like two currents meeting and bending each other. It matters because it can harden a binary and free energy into the surrounding cluster. A second mechanism follows from the first. An exchange interaction is a close encounter that swaps binary partners. It's like a heavier stone taking the deeper groove in a stream bed, while a lighter stone is carried away. It matters because a neutron star is very massive for its size. In an exchange, the neutron star tends to replace a lighter star in a binary. The binary survives, but its identity changes. The first micro payoff answers a quiet question. Recycling requires a companion that can feed the mass. Exchange interactions help provide that companion. A neutron star that is old and slow can be inserted into a new close pair. Once inserted, gas transfer can begin under the right conditions. The disk forms, spin rises, the millisecond rhythm returns. The physical detail of tightening is concrete. After an exchange, the orbit can shrink through further encounters. A tight binary is hard. A hard binary is a tight pair that grows tighter after encounters. It is like a knot that cinches under repeated tugs. It matters because tighter orbits make mass transfer more likely later. Tightness also raises the orbital speed. That makes timing effects larger and easier to detect. The one primary number sets a safe scale. In a crowded cluster core, a strong encounter can happen about once every million years, like the slow cycle of a glacier, reshaping a valley wall. That interval is long compared to any pulse. It is short compared to the age of the cluster. The scale shift is gentle. It moves from a millisecond tick to a million years between major orbital reshuffles. It then widens again to the full lifetime of the cluster. Over that lifetime, many reshuffles can occur. Each reshuffle is a new chance for recycling. The next payoff appears as a population result. Clusters can host millisecond pulsars with unusual companions and unusual orbits. Some orbits are very tight. Some are eccentric. Eccentricity is how stretched an orbit is. It is like an oval that refuses to become a circle. It matters because mass transfer usually circularizes orbits. When an eccentric recycled pulsar is seen, a later encounter is often implied. The encounter may have happened after recycling. It may have perturbed the orbit without undoing the millisecond spin. The visual cadence stays slow. Near the core, a binary sweeps an oval loop. Another star passes at a distance and the oval becomes slightly more stretched. The change is not violent. It is a new gravitational contour drawn into the orbit. Farther out, the cluster halo drifts with wider spacing and fewer close approaches. The brightness fades. The encounter rate drops. This adds another payoff. Location inside the cluster matters. The core is the engine room for exchanges. The halo is a quieter archive of old systems that have been scattered outward. Scattering itself is a physical story. Energy released from hardening binaries heats the cluster and can push stars outward. The cluster becomes a slowly breathing structure. The core can contract as it loses energy. It can also expand as binaries inject energy. The boundary between core and halo can shift over time. Another scale shift arrives without strain. It moves from the size of a binary orbit to the size of the cluster core. It then moves to the size of the cluster as a whole. Yet the millisecond pulsar remains the same small clock within each scale. The limit of observation now becomes clear and specific. Individual exchange encounters are not watched directly. The distances are too great. The timescales are too long. The evidence comes from present-day orbits and from population statistics. Many different encounter histories can lead to similar final systems. This is an inference limit. It is also a modeling limit. Simulations depend on assumptions about initial cluster structure and mass distribution. Timing can measure an orbit precisely. It cannot name the exact sequence of past encounters. The limit of intuition appears alongside it. It is tempting to picture the cluster as chaotic. The motion is complex. The outcomes still follow tendencies. Heavy objects sink toward the center over time. Lighter stars drift outward. Binaries act as energy reservoirs. These tendencies create a quiet order inside the apparent jumble. The next payoff is immediate. If many millisecond pulsars are found in the core, it suggests a history of mass segregation and repeated exchanges. If some are found far out, it suggests ejection from the core or formation in quieter regions. The distribution becomes a fossil record of dynamical life. The physical detail returns to keep the scene grounded. The core has a sharp gradient in stellar density. That gradient changes how often close passages occur. Near the center, orbits are cramped. Farther out paths are wider and encounters become rare. This is like a climate map made from gravity rather than air. A signal would carry the imprint of that climate through orbital eccentricity and companion type. Another micro payoff answers how this connects back to recycling physics. The same accretion processes still apply in clusters. Disks still form, polar caps still heat, magnetic burial can still occur. The difference is the supply chain of companions. In a dense cluster, companions can be replaced. Orbits can be tightened after recycling ends. The millisecond pulsar becomes a stable clock inside a changing family tree. The section ends with a soft transition toward a broader perspective. Cluster dynamics explains why many recycled pulsars live in these crowded spheres. The next section widens from clusters to the wider galaxy and to long-term evolutionary outcomes. It follows how recycled pulsars spread into different environments and how their timing remains steady across vast spans. A recycled pulsar leaves its birth site and carries its millisecond rhythm across the galaxy, like a quiet metronome in motion. The long afterlife is shaped by a weak magnetic braking, and by the slow widening or fading of its binary connection. In that region, the pulsar's environment is no longer a bright cluster core. It can be a sparse field of stars. It can be a thick disk with gas and dust far away. It can be a halo orbit that rises above the galactic plane. The first payoff is simple and immediate. Once recycling ends, the pulsar becomes an isolated clock or a clock in a quiet binary. Its spin changes only gradually. That gradual change is why millisecond pulsars can remain fast for immense spans. A concrete physical detail anchors the scene. The magnetic field lines near the star still form an organized structure. They curve outward and open beyond a boundary where co-rotation fails. That boundary is a light cylinder. A light cylinder is where co-rotation would reach light speed. It's like an invisible drumhead radius that sets the outer edge of orderly rotation. It matters because it shapes how particles accelerate and where radiation can form. The primary visual anchor is new and wide. The pulsar is a small dark point moving along a long arc above the faint glow of a galactic disk. The disk is a thin band with a soft dust lane. The pulsar's path is not a straight line. It is a slow loop around the galaxy. Along that loop, a narrow cone of emission sweeps like a quiet beacon. The cone is not a searchlight. It is a geometric consequence of rotation and magnetism. The analogy is calm and unique. It is like a well-made pocket watch carried through different rooms. The gears keep time the same way in each room. Temperature and humidity can change slightly. The design makes the drift small. In the same way, a recycled pulsar carries its timing stability through changing environments. The second core concept is magnetic dipole braking. Magnetic dipole braking is spin down from rotating magnetic structure. It is like a fan that slows because it pushes against air. It is also like a spinning top that loses energy to friction at its tip. It matters because it sets the long-term drift of the spin. For millisecond pulsars, the braking is weak because the surface field is weaker after recycling. The next payoff answers why the clock remains useful for so long. A weak break means the spin period increases slowly. The pulse shape can remain stable if the magnetosphere remains steady. The timing can then trace long arcs through the galaxy without losing its regularity. The third concept stays minimal and tied to binary fate. Some companions become very light. Some binaries become detached and quiet. Some systems become isolated if the companion mass loss continues. The details vary. The shared theme is gradual change rather than catastrophe. The one primary number anchors the timescale of the afterlife. A recycled pulsar can remain in the millisecond range for about 1 billion years, like a continental shelf, holding its shape through many sea-level cycles. This is a safe order of magnitude guide. It conveys persistence. The scale shift is gentle. It moves from a single millisecond tick to a billion-year drift. It then returns inward to the star's magnetosphere where small changes still matter. Another payoff arrives through geometry. As spin slows, the light cylinder moves outward. The open field region can adjust. That can change the size and position of emission zones. Pulse profiles can evolve slowly as a consequence. The evolution is often subtle. It can be detected when timing is precise. It can also be masked by propagation effects in the interstellar medium. A visual anchor appears on cadence and stays within the wide scene. The galactic plane looks like a dim ribbon. Between the pulsar and that ribbon, thin wisps of interstellar plasma create a faint refractive haze. The haze is not a cloud of dust, it is a changing distribution of electrons that can delay signals. The delay is frequency dependent, yet that detail remains implicit here. The key payoff is immediate. Timing must separate intrinsic spin drift from propagation delays. The separation is possible because delays change with line of sight and with path conditions. The spin drift remains coherent. The limit of observation now becomes explicit. The pulsar's trajectory through the galaxy is not measured by watching it move in real time. It is inferred from position on the sky and from timing changes. Distances can be uncertain. Small distance errors can change inferred velocities. The interstellar medium also adds delays that can mimic long-term trends if not modelled. This is a limit in measurement and modelling. It is not a failure of the clock. The limit of intuition arrives softly. It is tempting to imagine empty space between stars. The galaxy is filled with a thin plasma that is structured and turbulent. That structure can act like a slowly shifting lens. A lens can smear delay and reshape pulses. The clock is steady. The path is not always simple. Another payoff follows from that contrast. Because the pulsar is steady, the medium becomes visible through its distortions. Timing can map variations in electron content along the line of sight. It can also reveal large-scale structure in the galaxy's plasma distribution. The pulsar becomes both a clock and a probe. A concrete physical detail keeps the magnetosphere real. Near the star, the field lines form a bundle that opens into a fan. The bundle has a boundary where charge density changes sharply. That boundary can set where coherent emission forms. Changes in surface temperature and conductivity can alter the current distribution and shift that boundary. The shift can be gradual over long times. It can also be triggered by changing companion wind if a companion remains nearby. The story stays calm and avoids direct human framing. A signal would carry these shifts as tiny changes in profile and timing noise. Another scale shift widens again. It moves from the magnetosphere's boundary to the orbit of the pulsar around the galaxy. That orbit can carry the pulsar through different plasma environments. It can cross spiral arms where plasma density is higher. It can rise above the plane where density is lower. Each crossing changes propagation delays. The intrinsic clock remains. The end of the section turns toward the next arc without a new mystery. The long afterlife explains why recycled pulsars persist as stable beacons. The next section widens further to collective consequences. It follows how many millisecond pulsars together can form a galaxy-scale timing network, and how subtle correlated drifts can reveal deep background processes, then returns to a calm perspective. A single millisecond pulsar is a steady clock, yet many such clocks together can reveal a slower rhythm spread across the galaxy. A pulsar timing array compares timing residuals across many pulsars and looks for a shared pattern that cannot belong to any one system. In that region, the galaxy is not empty. It is a quiet sea of curved space-time with gentle disturbances that drift through. Each pulsar provides a line of sight through that sea. Each line has its own plasma delays and its own intrinsic noise. The first payoff arrives as a clear separation. Local noise differs from pulsar to pulsar. A shared gravitational influence would imprint a correlated pattern across the set. The correlation depends on the angles between pulsars on the sky. The primary visual anchor is new and calm. A wide galactic view shows many distant pulsars as faint points scattered across a dark sphere. Between these points, thin arcs connect pairs like soft threads. The threads do not carry energy. They represent comparisons of timing residuals. Across the sphere a slow ripple passes. The ripple is not visible as light. It is a gentle stretching and squeezing of distances that changes arrival times by tiny amounts. The analogy is quiet and unique. It is like a set of pendulums hanging in different rooms of a large house. Drafts and vibrations in each room differ. A slow sway in the whole building would nudge all pendulums in a related way. The shared sway is detected by comparing the differences, not by staring at one pendulum alone. The first core concept is the timing residual. A timing residual is the mismatch between predicted and observed arrival times. It is like a small discrepancy after aligning two musical beats. It is also like a drift line that remains after subtracting a smooth trend. It matters because it is where hidden influences appear. The second core concept is correlation. Correlation is a shared pattern across many signals. It's like seeing the same slow wave crest reach many buoys with a predictable lag. It matters because it distinguishes a global effect from local quirks. The third concept stays minimal and is named only once. A gravitational wave background is many overlapping weak gravitational waves. It is like a distant ocean made from many small swells. It matters because it can exist even when no single wave dominates. The next payoff clarifies what the array looks for. A background produces a characteristic correlation curve with angular separation. Pairs of pulsars separated by certain angles tend to share residual patterns with a specific sign and strength. This is not a sharp signature in one pulsar. It is a statistical imprint across many pairs. The key is that the imprint is geometric. It depends on sky angles, not on distance or brightness. The one primary number anchors the subtlety. The expected timing shift can be about 10 nanoseconds, like the time light takes to travel a few meters. This is an order of magnitude guide that stays safe. It conveys how small the effect is. The scale shift is gentle. It moves from millisecond pulses to a 10 nanosecond residual. It then widens to years of accumulated data needed to reveal a slow background. The story remains calm and procedural. Timing models remove known effects. Orbital motion is removed for binaries. Propagation delays are modeled and corrected. Spin-down trends are fitted. What remains is a residual sequence. The sequence is then compared across the network. Another payoff arrives through a simple picture of what a passing gravitational wave does. It slightly stretches space along one direction while squeezing along another. The stretching changes the effective path length for pulses. It can make pulses arrive slightly earlier or later depending on geometry. The effect is not constant. It oscillates slowly. The oscillation period can be years for the relevant frequencies. That slow timescale is why long observing spans matter. The visual cadence stays slow. The sphere of pulsars is shown again. The ripple passes. Some threads brighten to indicate positive correlation. Some threads dim to indicate negative correlation. The pattern is not random. It follows the angular geometry. Another payoff follows immediately. Because the pattern depends on an angle, it can be separated from errors in a time standard or from solar system modeling errors. Those errors tend to produce different correlation structures. This is the quiet strength of the method. It uses geometry as a filter. A concrete physical detail anchors the wave description. The wave changes the metric. That change acts like a transient strain field. The strain is not a force pulling objects together. It is a change in the distance measure itself. This is why intuition can stumble. The effect is not felt as a push. It is inferred from arrival times across enormous baselines. The limit of observation becomes explicit and specific. The array cannot point to a single source easily when the signal is a background. The data are noisy. Each pulsar has timing noise and profile changes. The interstellar medium adds delays that are not perfectly known. Model errors can masquerade as correlations if not controlled. This is a limit of inference and calibration. It requires careful cross-checks and long spans. It also requires a large sample of stable pulsars. The limit of intuition appears softly. It is tempting to imagine that a wave in space-time would be dramatic. In this frequency band, the waves are gentle. The effect is far smaller than any daily experience. The waves are sensed only because the pulsars provide exceptionally regular ticks over years. Another micro payoff answers why millisecond pulsars are essential. Their stability reduces intrinsic wonder. Their sharp pulses allow precise arrival measurements. Their distribution across the sky provides many pair angles. The network becomes a galaxy-scale instrument built from natural clocks. The story avoids human elements by keeping focus on signals and geometry. A signal would be delayed or advanced by a tiny amount. The delay would be different for different directions. The shared pattern across many directions is the key observable. Another visual anchor appears on cadence and remains within the same primary scene. A faint map of the sky is implied without labels. Points mark pulsar positions. Lines between points form a dense web. In some regions, the web shows a coherent, slow breathing. In other regions, it looks like independent jitter. The coherent part is the sought pattern. The jitter is the local noise that averages down with many pulsars and long time. The section ends with a soft transition that stabilizes the arc. The array concept widens the meaning of recycled pulsars beyond individual systems. The next section moves toward broader consequences and toward the quiet closing phases. It follows how these clocks fit into the galaxy's deep time story and how the narrative can settle into a final calm perspective. The galaxy becomes a calm archive when millisecond pulsars are seen as long-lived clocks that drift through changing neighborhoods. Recycled pulsars reveal the slow evolution of binaries and the gradual settling of stellar remnants into stable rolls. In that region, the scene is not a crowded core. It is a wide spiral disk with faint structure. Dust lanes draw soft, dark strokes. Star-forming regions glow as diffuse patches. Between them, older stars fill the background like a steady grain. The first payoff comes from a simple continuity. A recycled pulsar keeps its fast spin long after its accretion phase ends. That persistence means the present-day population still contains objects recycled in very old eras. The next payoff follows immediately. Population differences across the galaxy reflect different birth and recycling channels. Clusters enrich the central and halo regions with dynamically formed systems. The disk supplies many quiet binaries that evolve without frequent encounters. The primary visual anchor is new and gentle. A face-on view of a spiral galaxy shows curved arms like brushed paint. Scattered across that disk, tiny rhythmic beacons are implied by faint pulses. The beacons are not bright lamps. They are points of timing regularity embedded in a dim field. Their distribution is uneven. It is denser toward the inner disk, and in certain old clusters that orbit above the plane. The analogy is calm and unique. It is like a library with many clocks on different shelves. Some clocks sit in busy aisles and are handled often. Some rest in quiet corners and gather dust. The clocks still keep time. Their placement reveals how the building has been used over centuries. In the same way, the positions of recycled pulsars reveal how the galaxy has processed binaries and remnants over deep time. The first core concept is population synthesis stated in plain language. Population synthesis is modeling many systems to match observed populations. It is like mixing many recipes to reproduce the taste of a whole menu. It matters because individual histories are hard to reconstruct. The population can still constrain the average pathways. The second core concept is a merger of ideas already introduced kept minimal here. Binary evolution sets the supply of companions and accretion phases. Cluster dynamics reshuffles some systems and changes their outcomes. Together they shape where recycled pulsars appear and what companions they keep. The third concept stays optional and is used gently. A luminosity function is how brightness counts vary with brightness. It is like counting candles by their glow levels in a dark hall. It matters because detection favors brighter emitters and can bias the visible sample. The one primary number anchors the population scale safely. The Milky Way likely contains about 10,000 millisecond pulsars, like a city with many quiet clocks running behind walls. Most are not seen directly. Many beams miss the line of sight. Many are too faint at large distance. Many are masked by dense plasma along the galactic plane. The scale shift is soft. It moves from a single rotating neutron star to a population of 10,000 across a whole galaxy. It then returns inward to the details of selection effects that hide most of them. Another payoff arrives as a correction to a common assumption. The observed sample is not the full population. Beaming geometry selects which pulsars are visible. Interstellar scattering smears pulses especially toward the inner galaxy. Scattering is pulse broadening by plasma irregularities. It is like viewing a distant light through rippling water. It matters because a narrow pulse can become a wide blur and lose detectability. A visual anchor appears on cadence. Along a dust lane, faint ionized regions create a mottled veil. The veil is thin yet structured. A pulse train passing through the veil would be stretched in time and softened in shape. In clearer directions above the plane, the veil thins and pulses remain sharp. The payoff is immediate. The sky map of known millisecond pulsars is a map of both the population and the intervening medium. Another payoff follows from orbital variety. Some recycled pulsars have very light companions, some keep heavier white dwarf companions. The companion type reflects the duration and stability of the accretion phase. It also reflects the initial binary mass and separation. These differences matter because they reveal which pathways dominate in different galactic regions. Another visual anchor appears without repeating the main one. A quiet binary is implied as two dark points orbiting in a small ellipse. The ellipse is nearly circular. The separation is tiny compared to any stellar scale. The orbit is embedded in a wide field of starlight. The physical detail is the smoothness of the orbit. Tidal effects and mass transfer tend to circularize. When an eccentric orbit is seen later, dynamical perturbations are implied. The narrative keeps the tone soft and avoids sharp turns. The limit of observation becomes clear and specific. Distances are uncertain for many pulsars. That uncertainty affects inferred luminosity and inferred population totals. Selection biases are complex. Surveys have limited sensitivity and frequency coverage. Scattering and dispersion vary across the sky. These limits mean population estimates depend on models. Different assumptions about beaming fractions and luminosity distributions can shift totals. This is a modeling limit rather than a simple measurement error. The limit of intuition follows gently. It is tempting to imagine a galaxy filled with uniformly distributed clocks. The real distribution is lumpy and shaped by star formation history and by dynamical reservoirs like clusters. The path from binary to recycled pulsar is also not guaranteed. Small changes in initial masses and separations can produce different outcomes. That branching makes the galaxy's archive subtle. Another payoff appears as a stabilizing insight. Even with biases, certain patterns remain robust. Recycled pulsars concentrate in old stellar environments. They appear in globular clusters at enhanced rates. They populate the galactic disk in regions where binaries have had time to evolve. These patterns align with the idea of recycling as a long conditional process. A concrete physical detail returns to the neutron star itself. The polar cap region remains small and hot compared to the rest of the surface. The magnetosphere remains structured by open and closed field line regions. These structures persist while the star ages. They provide the stable geometry that supports long-term timing. The story ends with a soft transition that prepares for a gentle resolution. The galaxy-scale archive shows why recycled pulsars matter beyond their individual clocks. The final section turns inward toward a quiet synthesis. It returns to the millisecond rhythm as a calm thread through deep time and settles into a stable, restful closing. A millisecond pulsar is a quiet endpoint of violence that now behaves like a steady metronome in deep space. The recycling process leaves behind a long-lived balance between spin magnetism and a stable beam geometry. At this distance, the scene begins close to the star and then slowly widens. The surface is a compact sphere with a thin atmosphere and a hard boundary. Near each magnetic pole, a small polar cap stays warmer than the surrounding crust. Above it, plasma follows curved magnetic field lines. Some field lines loop back and close, some open outward and guide particles away. The first payoff is simple and settling. The beam is not a physical lighthouse lamp. It is a pattern of radio emission tied to the magnetic geometry. Rotation sweeps that pattern through space with clock-like regularity. The primary visual anchor is new and gentle. A single neutron star drifts in a dark region with sparse starlight. Its field lines are traced as faint arcs that curve away and return. A narrow emission cone is implied as a soft shape that rotates without strain. The cone skims through the surrounding darkness like a slow fan. Each pass is a pulse. The pulses are not heard here. They are a rhythm that could be counted. The analogy is calm and unique. It is like a long pendulum clock sealed inside a quiet room of stone. Air currents are minimal. The swing is steady. Over long nights, small drifts become measurable, yet the basic cadence remains. In the same way, a recycled pulsar keeps time across eras, even while its environment changes. The first core concept is spin stability. Spin stability is the persistence of a nearly constant rotation rate. It is like a wheel that keeps turning with almost no wobble. It is also like a song tempo that barely drifts between verses. It matters because a stable spin turns the pulsar into a usable clock. The second core concept is magnetic braking in its mild late form. Magnetic braking is the slow loss of spin through electromagnetic torque. It is like a gentle drag on a spinning top. It is also like a faint resistance that lengthens the period over long time. It matters because it sets the long-term aging of the clock. The third concept is used only once and kept plain. Beam geometry is how the emission pattern is shaped and oriented. It is like the cut of a moving spotlight, yet without a lamp. It matters because visibility depends on orientation, not on power alone. The one main number anchors the final scale shift. A typical millisecond pulsar spins about 300 times per second like a hummingbird wing beat compressed into a single point of rotation. This number is a safe order of magnitude. It helps the mind connect the word millisecond to a physical cadence. The scale shift follows gently. It moves from a 300 times per second spin to years of timing. It then widens to billions of years of survival for the neutron star itself. The next payoff arrives in how recycling changes magnetism. Accretion can bury and smooth parts of the magnetic field. That can reduce the field strength compared with young pulsars. A weaker field means a gentler braking torque. A gentler torque means the fast spin can persist for a very long time. The story settles into a calm causal chain. Spin up occurs during accretion. Spin down resumes after accretion ends. The balance between them defines the recycled state. A visual anchor appears on cadence within the same scene. The star's polar cap region shows a sharp boundary where temperature and particle flow change. The boundary is not fuzzy. It is a gradient over a small distance. The gradient shapes how charges accelerate and radiate. The pulse shape depends on this structure. A slight change in geometry can shift the pulse profile. That is why timing models care about stable shapes. Another payoff follows immediately. When the pulse profile stays stable, arrival times can be measured precisely. When the profile changes, timing noise grows. The causes can include magnetospheric state changes and propagation effects in interstellar plasma. In that region, the interstellar medium is not smooth. It has filaments and clumps that cause dispersion and scattering. Dispersion is frequency-dependent delay by plasma. It is like a low tone lagging behind a high tone in a distant echo. It matters because timing must correct for it to preserve the clock. A gentle limit of observation is stated with clarity. The clock is not read directly from a dial. It is inferred from pulse arrival times at a distance. Those times are altered by plasma along the path. They are also altered by orbital motion in binaries. They are altered by gravitational influences on the path length. Separating these effects requires models and long data spans. This is a limit of inference and of calibration. It is not a failure of the pulsar. It is a constraint on what can be extracted from the signal. The limit of intuition follows softly. It is tempting to imagine the pulsar as a perfect stopwatch. In reality, it is a physical object with changing plasma states. Even small magnetospheric shifts can alter pulse shapes. Those changes can mimic timing drifts. This is why ensembles and cross-checks matter. Another micro-payoff resolves what recycling ultimately provides. Recycling produces a clock that is stable enough to probe subtle phenomena. It can trace binary evolution. It can test gravitational theories through orbital decay and timing geometry. It can contribute to galaxy-scale timing arrays that sense slow space-time disturbances. These capabilities arise not from power, but from regularity. A final visual anchor closes the loop. The star's beam sweeps through darkness in a slow, patient rhythm. Far away, other recycled pulsars add their own steady beats. The galaxy becomes a quiet field of timing. The beats are not synchronized like a choir. They are independent, yet each is stable. Together they form a calm fabric of reference points in a changing universe. The closing transition is gentle and complete. The recycled pulsar remains as it is a compact remnant with a fast spin and a softened magnetic grip. The script settles into silence around that steady cadence. The last pulses continue without urgency and the narrative rests alongside them.